Hey, and welcome back to another LeetCode video. Today I'm going to show you how to solve LeetCode 987, vertical order traversal of a binary tree. And it's a hard problem, and it's a super interesting one because you rarely see vertical order traversal of a binary tree. So let's just get into this, understand the problem first, and then I'll show you how to solve it. Well, we're given only the root of a node, and when you look at the node, you have, basically every node gets a coordinate attached to it. The root node is at the coordinate 0, 0, which corresponds to row 0 and column 0. And when we go down a level, we increase the row. And when we go right, we increase the column. When we go left, we decrease the column, like so. And our task is to find all the nodes and group them by the column so that we can emit them by column. Here you can see the first column is the one that contains node 1. That's column -1. The second column is at 0, column 0, that contains the node 3 and 15. Then we have this column that just contains 20. And finally, we have the column that contains 7. So this is how we should output them. Nodes that are in the same column are added as an array and emitted as such. Now, what can happen is that you have two nodes that are in the same row and same column. And in this case, we should sort them, right? That's pretty much what we should do. And append them in the order. This actually states here explicitly. There may be multiple nodes in the same row and same column. In such case, sort these nodes by their values. Right, and so that's what we're going to do. Cool. Well, that's the whole thing, right? So, well, how do we approach this? I would suggest we use a level order traversal. And, well, actually, we don't even have to care about the level order traversal. We can also just use a recursive one. Yeah, why not? Let's implement a recursive solution. So we will just iterate through our tree, and we will keep track of in which column and which row we are. And we're just going to collect all of the nodes, and we're going to stuff them into a hash map that has the column as the key, right? So let's see. So we say column. Well, yeah, we need hash map first. Column values is a hash map, and maybe just make it a default dict, and we just make it have lists. Cool. And then we just, well, what else do we need? Well, we need some way to traverse the dictionary, the tree, and we're going to use a deck for that, right? Deck. And our seed will be the root node at, I suppose, column 0, right? Then we have our little while queue, which we will always have when we iterate through a tree. And so while we have elements in the queue, we're actually going to iterate over all of the elements that are on the current level. Length queue. And we're going to pull out the node and its column, top left. And then, well, we need to update our column values now. Well, and we're going to, well, at column values, at key column, we're going to append. What are we going to append? Well, we should also keep track of the row, right? So we start at row 0, and we're going to append the row and actually the node value. Those are the two things that we append. That'll help us with sorting later on. And then we have to make sure that we increase the row after iterating through the current level. And we now have to process the left and the right node. So if node.left, well, in this case, we're going to append that to the queue. And we're going to append an array of node.left and column -1. Same for the right child of the node, except this time we're going to append, we're updating the column value with +1 because we're making one step to the right. Cool. So that is how we traverse the entire tree. And now we have to collect the results again. And how do we do that? Well, result is going to be an array, right? And as you see here, it's an array of arrays. And each array in here corresponds to all the values that we have in one column. So now, since we used a hash map to store these values, and I forgot to mention this, but we're using a hash map here because, well, we could use an array, but then we would have first to calculate what is the width of our binary tree, because we don't know how far to the left or how far to the right we're going to go. We don't know what the min and the max column value is. So if we use this columns value as a hash map, we can just determine what the min column is. And that's just the minimum of the keys of that hash map, right? And yeah, that's pretty much it. So the keys. So we could just do it like this. And we can also compute the max. And now we just iterate over them. For call in range, min call, to max call, of course, +1, because the end of the for range is not included in the values that call loops over. So now we come to sorting. Well, what about this? Sorry, column values. At position, at column. Well, we sort them. And remember, what have we inserted into those values? We have inserted the row first and then the value. So that's actually how they're also going to get sorted. First by the row and only secondly by the value, right? And that gives us exactly the sorting that we really want. And now we just need to basically get the values out. So values. And since we're storing rows and node values, we kind of have to, well, get them. We're going to, for val in val, what? For val in, or in column values at the column. Right, so that should be the whole thing. Well, now let's think about, well, let's just run, see if the tests pass. Right, so the tests pass. Well, you still have to do a complexity analysis. Okay, cool. All tests actually pass. So, well, what are we dealing with in terms of time and space? Well, in space, well, we know we have n nodes, right? Space means, well, we're going to store a value for every node that we encounter. So we can say we have O of n space. Now with time, well, technically speaking, we are visiting every single node, but also we have to do some kind of sorting, right? So the sorting now, this sorting is O of k log k, where k is the length of the array that is being sorted. So now the question is, how long can these column values become, right? So if we take, let's start with this tree, and if we put it here, like so, how many nodes can we get in the same column, right? Right, at, let's say at column 0. So this is all column 0. Well, every time we go, so since they are in the same column, the right child of each node is also going to be on the same column, which is going to be column 1. Same for the left child of these two nodes. They're also going to be at column -1. Now, their children again, if we now have 2 nodes and we take their right child, that gives us 2 that will be at column 0 again. And we get 2 more at this column, right? So we start out with 1 node at column 0. Now we have 2 nodes at column 0. Now we've got 4 more at column 0. And this just continues on and on and on. And at every 2 height steps, we will double this number. So we have 1, 2, 4. Next time we get 8, right? Yeah. And this is kind of, there's a little bit of an exponential growth that is happening here. Now the question is, how large is that going to get? So that obviously depends on the height of the tree and the number of nodes. So in the worst case, we will have a tree that really only has this, where a node has a left child and that left child only has a right child. And on the other side of the tree, so if you mirror that, you have the same thing. You could even think about a tree that really goes always just like this, left, right, left, right, left, right. So that would mean you have at most n over 2 nodes on the same level. At the same level. Sorry, at the same column. Now, if we think about the other half here, that doesn't really change the math, right? It's still going to be exactly the same. It's still going to be exactly the same. Just that, you know, the height of this pattern is just going to be shorter, but still going to be at most O of n nodes that we will have in the same level. So in the worst case, we have an n log n to sort all of the nodes that are exactly in the same column. That's why the runtime complexity becomes n log n, and n plus, we can remove that. So yeah, I think that's the analysis, n log n time and O of n space for the vertical order traversal of a binary tree that has the requirement to sort nodes that are on the same row and the same column as we've seen here. Right, that concludes this problem.